Once the geometry of the model is completed, including the loads of the elements and materials, we are ready to launch the structure calculation. The calculation phase is managed as we have seen previously from the calculation menu, and it is possible to launch it in steps. This other step of the calculation in order: structural model and framework. Stresses. Verifications and checks. Reinforcements. Flaws calculations. Finally, we can launch the full calculation that includes all the structure calculations. At the end of the first phase of the calculation, the structural model and frameworks, it is possible to view the structural model, generated automatically by the software. This is a 3D model, in which 2D elements, such as walls, have been synthesized to triangular shells. Possible one-dimensional elements such as beams in both reinforced concrete and other materials, are schematized as beam elements. This is the model that will go to the finite element calculation engine. We can see how the program manages the distribution of the shell and consequently how it considers each eccentricity by calculation of the finite elements. This model returns tensions for the elements represented in shell. The software also has a piers and bands view of the structure. Accessing this visibility of the model, and selecting a piers, we notice the presence of horizontal sections. When we select the bands, we see the presence of vertical sections. Earlier we said that the shell model involves a calculation of the tension, defined for the bands and piers. Horizontal and vertical sections represent these stresses and general stresses such as bending moments, shearing, and normal forces. Then by selecting the elements in the model we will obtain the verifications required by norm. In addition to the calculation, we can know the structure's response to the different actions. As a result, we can know in advance and check through the 3D view, the overall results that affect the entire model. For example, we can see the displacements that occur due to the structure's own weight. We can also consult the general or specific stresses in certain elements. In this case we see the bending moments of the beam elements present in the structure. As for the two-dimensional elements, i.e. shells, like the walls, we can consult the stresses. At the local level we can clearly access the piers view, select one or a band and see the verification in the plane, at the bending, etc. Once the calculation has been made, we know that the software offers us a general diagnosis. This diagnostics may present error messages, which should not frighten the technician. Especially when we work with existing structures. It is very simple to work through diagnostics. By double-clicking on one of these messages, the program leads us to the pier in error, and from the Properties toolbox within the Results field we can consult the verifications. In this case, we have the shear verification that has a safety coefficient lower than 1, and for this it is reported in the diagnostics. Let's now see how to act on this diagnostic. When we are testing a new structure, once the calculation is launched, the diagnostics must be without error messages, since the structure must support 100% of the actions required by the regulations. Similarly, when working with existing buildings and the project is a seismic adaptation, the goal is to support 100% of the actions. So once again, while working in design stage, we need to ensure an error-free diagnosis. Instead, when we are evaluating the state of the structure of an existing asset for an improvement of the structure, we can accept that the diagnosis presents some errors. This is because the reported errors refer to maximum seismic actions. When the object is simply a structural improvement, we do not have to guarantee that the structure tolerates 100% of the seismic action. So in that case we accept the error message of the diagnosis. We will evaluate the capacity of the building in the current situation or in the design stage by checking the collapse accelerations. In the 3D view we access the results. For example, for masonry, if we indicate the shear in the plane, the chromatic scale shows the relationship between capacity and resistance expressed in terms of percentage. Applying a filter, by raising the bar to 100, we instruct the program to show us all the elements with a smaller capacity in the 3D view. Starting from the collapse accelerations with respect to the various mechanisms, the relationship of the seismic behavior is reported. In any case, the collapse accelerations are calculated, not only for the flexor compression and shear mechanisms, but they are also calculated for the local mechanisms. Keep in mind that the software carries out these checks when we add to the model the element called facade, calculation section. By means of this element and with respect to this facade, the software carries out the checks both for toppling and bulging. If we access the Results tab, we can consult the checks, in this case on the toppling of the facade. We see that a check is indicated in error. If we just check the position of the chains, we can easily see that the error is linked to the possible formation of a hinge where the chains are positioned, and that this error is linked to the upper wall of the facade. When we add the chains to the model, we obviously have to return the punching, shear and traction verification with the wall. The calculation of these parameters depends on where and how the chain was positioned. In this case, the chain was positioned in a reinforced concrete edge beam. Consequently, the shear and punching resistance takes into account the characteristics of the concrete, and therefore we see a greater contribution than a chain positioned on the wall. If we consider the structural model at the shell elements in which the chain is located, we see a reinforced concrete element. So this model allows us to differentiate the types of materials in a quick and local way. Same as if we go to 3D views and see a window in the shell's environment, the elements near the opening are characterized by different materials. So this shell view allows us to have a local characterization of the materials. Starting from the calculated collapse accelerations, the software elaborates a document that is particularly important as a summary document. The vulnerability sheet. In this sheet we find a preliminary summary of the main parameters, such as seismic hazard, a summary of the level of knowledge of the structure, materials, and so on. If we go to Table 9, this contains a summary of the capabilities. In this case it is evaluated with respect to the various limit states, both the concrete and masonry elements, as we can see in the second column. Therefore, the capacity in terms of seismic acceleration is indicated for each mechanism. The minimum capacity indicated at the stress gives us the seismic risk indicator. In this case we remember that the project is a project state for which the safety index indicates the capacity.